Okay, welcome to this CoilDesigner webinar. The purpose of this session is to review model validation and some of the techniques and tools that can be used to tune our heat exchanger models within the CoilDesigner environment to better match experimental data. My name is Dennis Masuda, and I'm joined by my colleague Paul Kalmowski. In this session, we'll discuss some of the fundamentals of modeling heat exchangers within the CoilDesigner software and review some of the basics of the modeling approach. Then we'll discuss a systematic technique for tuning our heat exchanger models to match experimental data that we may have collected. And then the remainder of this session will be focused on some example case studies to demonstrate techniques that can be used to tune heat exchanger models based on varying sets of experimental data that may be available to you. As a high-level overview, heat exchanger modeling within CoilDesigner follows the finite control volume technique, meaning we take a heat exchanger and divide it into a number of control volumes, as you can see here. And within each of these control volumes, we perform mass and energy balances to determine the outlet state of the air and refrigerant fluids. Within each segment, we're doing the epsilon NTU method for energy balance to determine the heat transfer between these two fluids. And in order to determine the actual convective heat transfer on either the external fin surface or the internal tube surface, we're using empirical correlations to predict heat transfer coefficients. So we're not directly using laboratory data for this heat exchanger. We're not running numerical CFD simulations, but we're relying on these empirical correlations, which are essentially curve fits of a number of experimental test points to predict the heat transfer and pressure drop in each segment of the heat exchanger. And when we take this approach, we have the susceptibility to some uncertainty just due to the fitting of those correlations and some of the differences between heat exchangers that may have been tested empirically in the past compared to the actual values that we would experience with our particular heat exchanger. So this is exactly the reason why we need to do model tuning of a heat exchanger, because these correlations are just predictions of heat transfer and pressure drop on our air and refrigerant surfaces. And sometimes when there are differences in manufacturing processes or geometry details, we can get different results. So the purpose of this session is to discuss how can we tune these characteristics of the heat exchanger performance to better match what we know to be true from experimental data. As a quick overview, this slide summarizes two of the techniques that can be used to model a coil within CoilDesigner. At a high level, we basically tasked with solving a heat exchanger with either inlet or outlet data for the streams that are flowing out of it. The most basic scenario is where we know the inlet conditions coming into the heat exchanger. We know the air inlet pressure, temperature, and flow rate, but we also know the refrigerant inlet state and mass flow rate. And if that's the case, we can set those conditions into the inlet streams of CoilDesigner through the interface and run the simulation. And this is the most basic and common technique to using CoilDesigner. But there's also an outlet conditions function, solve for outlet conditions function within CoilDesigner that allows us to iteratively solve for mass flow rate when we don't know that value. So in this scenario, we know the refrigerant outlet state that we require and some information about the refrigerant inlet enthalpy, but we don't know the refrigerant mass flow rate. And so we can use this iterative solver to determine mass flow rate based on the superheat or subcooling that we've observed. Now, when we're talking about model validation, we really strongly recommend that we follow this first technique where we have a fixed refrigerant inlet condition specified before any model tuning is applied. And this is really important because when we have a mass flow rate defined, we're able to tune the heat transfer and pressure drop parameters of the heat exchanger with a fixed mass flow rate. Whereas if we don't know the mass flow rate and we use the iterative solver, each time we solve this heat exchanger model, we may end up with a different mass flow rate. It makes it very difficult to tune heat transfer coefficients and pressure drops coefficients when the refrigerant mass flow rate or air mass flow rate is not fixed. So just as a brief reminder that we recommend that we begin with fixed refrigerant inlet conditions and mass flow rate when performing any model tuning. The next slide summarizes a systematic approach for tuning a heat exchanger model within CoilDesigner. This isn't the only way that this tuning can be performed, but it's an approach we recommend because it's consistent, repeatable, and simplifies the process. So when we begin tuning a heat exchanger model, we start by entering all of our information into CoilDesigner, the geometry, the flow configuration, and so on. And before we begin any model tuning, we want to double check all of the details of the coil. We want to make sure the geometry has truly been entered correctly. We want to double check the inlet conditions, all the correlation selections that have been made, make sure that this model is correct. Because if there's a mistake, there's no value in tuning the heat exchanger model based on those conditions. We'll start by running the simulation and review the results. The first result that we're going to assess is the refrigerant pressure drop, here written as RDP. If the refrigerant pressure drop is not well matched by the model, or we're comparing against the experimental data, then we need to apply some correction factor to the refrigerant pressure drop correlation. Now, there are three different refrigerant pressure drop correlations for every heat exchanger for all three phases, liquid, two-phase, and vapor. We recommend, for simplicity, applying the same correction factor across all three phases. So if the heat exchanger model in CoilDesigner is predicting a refrigerant pressure drop that's much higher than we observed experimentally, we would apply a correction factor that's less than 1. In the other scenario, we would apply a correction factor that's greater than 1 to inflate the refrigerant pressure drop prediction. We'll iterate through this process until we find a refrigerant pressure drop that is okay, that matches our experimental values well. We want to target that being at least within 20%. And because we can update the correction factor, we can really tune this value to match as closely as we can get it. Once the refrigerant pressure drop has been tuned, we move on to checking the heat exchanger capacity. So we check to see if the capacity of the coil is consistent with what we observed experimentally. Before we tune anything, we want to double check our inlet conditions. Oftentimes we may find if we have a very different prediction of capacity than we saw in the experiment, that there's been some error in entry of refrigerant inlet state on mass flow. And if any of these conditions are unknown, it's really important that these values be determined with certainty before we begin tuning the heat exchanger model. Once we're satisfied that the inlet conditions and all geometry and details of the heat exchanger has been entered completely correctly, then our recommendation is to apply a correction factor to the air side heat transfer coefficient. And what this can do is influence the overall heat transfer rate of the heat exchanger. The air side heat transfer resistance is the more significant resistance when compared to the refrigerant side heat transfer coefficient and the conduction through the fins and tubes. So we get a greater effect by applying a correction factor to the air side heat transfer coefficient, a bigger effect on the overall coil capacity. So again, if our capacity is low, we might apply a correction factor that's greater than 1. If our capacity from the simulation is too high compared to the experiment, we would apply a heat transfer coefficient correction factor that's less than 1. And we'll iterate through this process until the heat exchanger capacity matches well with the experiment. The next step is to match the superheat over subcooling. It's possible to match the heat exchanger capacity very closely, but still be very far off in predicting the superheat or subcooling, because the heat transfer contribution of that superheated or subcooled region is comparatively small to the two-phase region of the coil. So again, we'll check this value for superheat or subcooling. If it's not accurate, we again want to double check refrigerant mass flow rates. In some cases, when this number is very far off, we find that there's some mismatch, and the refrigerant mass flow rate that's being specified couldn't possibly achieve the superheat or subcooling that's being requested. Once everything's to our satisfaction, we can continue to update that air heat transfer coefficient correction factor, and this is fine-tuning until the superheat or subcooling is matched. Next, we'll check the air outlet temperature, which, if our heat exchanger capacity is accurate and our air flow rate is accurate, our air outlet temperature must be correct. If that's not the case, we need to double check our airflow rate, and we need to double check our air inlet temperature relative to humidity. this will reveal some inconsistency if the air outlet temperature is not correct and other characteristics of the coil are correct. And then finally, we'll look at the air side pressure drop, and we can apply a correction factor to the air side pressure drop correction factor field in CoilDesigner to increase or decrease this value. Once all of these criteria have been met, we should have a model that's predicting all of these values to our satisfaction at the same time. And before we complete our effort, we want to just assess all the correction factors that we've had to apply so far. We want to see if they've been very high or very small. For example, if they're greater than 1.5 or less than 0.5, this may be a warning sign that we really had to apply severe tuning to the heat exchanger model to get it to match our experiment. And that could indicate some issue with the applicability of the correlation that's been selected, or even issues with the experimental results. So we'll double check all of the details of the coil that we modeled and the measured values that we collected if we have these red flags showing up that a very high correction factor is needed. Otherwise, we consider this to be a success, and we have a model that should be accurate at the conditions that we've tested, as well as conditions outside of that range. So with that, we'll move into our first case study. In this example, we're going to look at an evaporator coil. It's an A coil, and uniquely it uses carbon dioxide as its refrigerant, and has tubes with a diameter of 5 millimeters. For simplicity's sake, we're going to just model half of this heat exchanger. We're going to treat it as symmetric, and we're going to make the assumption that airflow rate is uniform, although in reality, because of that A coil geometry, airflow rate is not going to be uniform. And then we're going to apply heat transfer correlations as specified in this table. And we have an example of this heat exchanger modeled in CoilDesigner that we will work through. But before we can begin tuning the model, we need to understand some of the inlet conditions and the performance information from this coil that we're trying to match. So in this case, we have a limited set of laboratory data. It's not all the time that we have every single detail that we need coming out of our lab report. Sometimes we have very limited information from our vendor or from our laboratory, and we have to figure out some of the details of what's really happening in this heat exchanger before we can perform model tuning. So, for example, in this case, we know the evaporating temperature, the liquid temperature, the superheat, the subcooling temperature. We know how much pressure drop occurs across the coil. And on the air side, we've measured the capacity. But on the refrigerant side, we don't know the refrigerant flow rate. And so we have to take some steps to determine what is that inlet flow rate before we can begin tuning the model. And what we'll do is we'll show how we can calculate these values with thermophysical properties of the refrigerant. And Paul will show an example of this in Excel.
If you don't know all input parameters for your CoilDesigner model, we recommend to use a third-party software such as EASE or RefProp to calculate them. At Optimized Thermal Systems, we use the software called XProps. XProps uses the RefProp database for the refrigerant properties. XProps can be used with different software such as C#, Visual Basic, and Microsoft Excel. I'm going to show it to you how we use XProps in Microsoft Excel. So I'm going to insert functions. In the drop-down menu, I'm going to select XProps refrigerant properties. And in the properties list, I'm going to select the dew point pressure. Okay, I'm going to use the carbon dioxide as a refrigerant with the English units. And I'm going to select the evaporating pressure. As you can see, XProps calculated the evaporating pressure by using the evaporating temperature. In exactly the same manner, I calculated all other refrigerant properties, such as condensing pressure, enthalpy at the condenser outlet by using the temperature and pressure at the condenser outlet. I assumed that the expansion is isenthalpic. That's why the enthalpy at the condenser outlet and evaporator inlet are exactly the same. I calculated the enthalpy at the evaporator outlet by using the pressure and temperature at the evaporator outlet. I calculated the vapor inlet quality by using the evaporating pressure and enthalpy at the evaporator inlet. And I calculated the refrigerant mass flow rate by dividing the air side capacity by the enthalpy difference in the evaporator. Now we have enough input parameters for our evaporator model. I'm going to enter them into the CoilDesigner model. Vapor quality and the mass flow rate, confirming selection, and run the simulation model.
So here we have the updated table, including the values that Paul has calculated based on the observed values using the thermophysical properties of carbon dioxide. Now that we have these values determined, we know the vapor inlet quality at the inlet of the evaporator and the refrigerant mass flow rate, so we can specify our inlet state coming into CoilDesigner. After we've simulated this coil once, we can begin to assess the performance of the heat exchanger model against our experimental data. So in this first table, we'll show our comparison of these key parameters, our capacity, experiment versus our simulation value, the air outlet temperature, refrigerant pressure drop, air pressure drop, and superheat. And right off the bat, most of these parameters are looking very good. They seem to be well predicted by the model without any significant tuning. But when we focus in on this, we can see a couple things that could be improved. Our refrigerant pressure drop has been underpredicted by about 20% in the simulation compared to the experiment. And also our superheat, our simulated superheat is much higher than what was experimentally observed. So these are the two areas that we focus on. So starting with the refrigerant pressure drop, when we look at this, the value that's reported from CoilDesigner, you can see we're about 20% too low. And if we look at this ratio, the actual value to the simulated value, it's about 1.24. We can actually just directly apply that ratio as our correction factor to the refrigerant side pressure drop in CoilDesigner. So there are three fields for entering those refrigerant pressure drop correction factors. When we apply that, this is the result that we get after we simulate them once more in CoilDesigner. So we've inflated the predicted refrigerant pressure drop by about 24%, and as a result, we have a pressure drop that's matching much more closely to our experimental value. And we can continue to fine-tune this, but typically this is a very simple approach to tune something like refrigerant or air side pressure drop. The next thing we're going to look at is the superheat of the coil, which is an over-predicted by our model. To find an appropriate correction factor, we can go back to our flow chart, and we know that we want to apply correction to the air side heat transfer coefficient to make the heat exchanger more or less effective, to have some influence on the superheat of this evaporator. And so this plot shows a simulation from the CoilDesigner run with correction factors from 0.5 up to 1, and the subsequent superheat that's predicted from those simulations. And if we look to our 10 degrees superheat, which we saw experimentally, we need to apply a correction factor of 0.63 to the air side heat transfer coefficient in order to match that superheat. So this is a pretty significant correction factor that needs to be applied. And it wasn't immediately apparent when we looked at the coil capacity. Without any correction, our coil capacity was well predicted, but this superheat was really over-predicted, which is a subtle but important difference that needs to be corrected. So why is this heat transfer correction factor so significant? Well, in this case, our fin geometry is not well known. We can make some guesses about the details of the enhancements of those fins. We have air maldistribution in the actual coil that was experimentally tested compared to our model, which assumes that it's completely uniform. We're also applying CFD-based correlations that have not been experimentally validated. So all these things together mean we don't have a great deal of certainty in the predicted value of heat transfer coefficient, but we also have these other effects that we're compensating for, this air maldistribution. We're simplifying this flow, treating it as uniform, when in reality it's not. But once we do apply this correction factor to the airside heat transfer coefficient, we're able to match the superheat much more closely, and all of our other parameters remain acceptable. So, we now have a superheat that matches 10 degrees to our experiment, but also our total capacity, outlet temperatures, all these other parameters remain to be well predicted by the model. So this has been a successful tuning by just influencing two of these correction factor values. In this next example, rather than showing how to tune a heat exchanger model for one single test point, we're going to look at what happens when we have a whole series of test points for a particular heat exchanger. So in this case, we'll talk about tests that were performed on some tube fin heat exchangers with 5mm tubes. They have water being used as the refrigerant in liquid phase, and this is common practice when we want to determine heat transfer coefficients of a tube fin surface. To run these tests, we ran 3 different airflow rates, but also 3 different water flow rates for each of those airflow rates. And these are everything, all these conditions are being controlled very carefully within the wind tunnel facility. So looking at just one of these heat exchangers, this is what a test report might look like for a particular coil. There are 9 test points, and for each of them there are 3 airflow rates. For each airflow rate there are 3 water flow rates. And from our experiment we've measured all of the important flow conditions as well as the outlet temperatures, pressures, as well as the coil. From this information, we can then begin to do some analysis of the predicted values from CoilDesigner and how they compare across all 9 points that were tested experimentally.
I'm going to show to you how to calculate a correction factor for the air pressure drop for the entire series. First of all, I need to set the inlet parameters. I used the inlet parameters for the first test, but you can use the parameters for any of the tests, confirm the selection, and run an initial simulation. After the initial simulation is done, then you can use the parametric analysis in CoilDesigner. So I'm going to run a parametric analysis for 9 points because we have 9 tests. I'm going to use the single phase as the refrigerant state because we're using liquid water. And as the input parameters, I'm going to select air temperature, air relative humidity, air flow rate, refrigerant temperature, and the refrigerant flow rate, the table. To save some time, I already created a table with all input parameters, so I can just copy them and paste in CoilDesigner. And now I can run the parametric analysis. Okay. After the calculations are done, I can export them to an Excel spreadsheet. To calculate the most suitable correction factor for the airside pressure drop, I created a separate table. The first row contains the measured pressure drop. The second row contains the calculated pressure drop. The third row contains the calculated pressure drop multiplied by an arbitrary correction factor. In this case, it's 1.05, but it could be any other correction factors. Also calculated the deviations from the test data, and I calculated the squares of the deviations on the errors. Finally, I calculated the sum of the squares. So in order for me to find the optimum correction factor, I needed to minimize the sum of the squares, and I can do it by using the solver in Microsoft Excel. So my goal is to minimize the sums of the squares, and by changing the correction factor, which is located in this cell. Click solve. So as you can see, CoilDesigner calculated the most suitable correction factor, which is 1.03. You can use this correction factor for any other simulations in CoilDesigner.
So as Paul demonstrated with the airside pressure drop correction factor and how we can use the Excel solver to minimize the error across all 9 test points, we can do some similar work to tune the heat exchanger capacity, although we can't just linearly affect the airside heat transfer coefficient to get the result we want in terms of overall heat exchanger capacity. So we can again use the parametric study feature within CoilDesigner to take all 9 of these test points and simulate each one at multiple correction factors. In this plot, we show all 9 test points simulated with correction factors ranging from 0.6 to 1.2. We show the simulation result compared against the experimental result to find the correction factor that gives us the least error for all 9 points when considered as a whole. If we take all of these errors and we take the sum squared error value for each series of 9 test points, or each correction factor, then we can find the point where the correction factor gives us the least error for all 9 points. And that happens right around here at 0.76 airside heat transfer coefficient correction factor. At this point, you have the least error in considering the whole data set. And again, we look at our initial results here from the original simulation comparison against our measurements, and we compare that to the simulation results when we apply the 0.76 correction factor. We do indeed see a reduced sum squared error from all of these points. We can see that for a larger portion of these points, we have very low error, with a small portion of these having higher error. So cumulatively looking at all of the points, we have a better fit across the entire data set. So that wraps up this session on heat exchanger tuning to match model results against experimental values. So we'll leave you with a few suggestions moving forward. First of all, it's important to always determine all of the inlet and outlet states, the mass flow rate, everything that we need to characterize the performance from a test before we begin tuning models. There's no sense in performing this work if we have an unknown value like mass flow rate or capacity, if we're taking guesses as to the operating conditions of the equipment. And if we don't have certain conditions, as we showed in our first example, we need to model the cycle and calculate the thermophysical properties of the fluid using some other software. It could be XProps, it could be Ease, RefProp, some other tool that allows us to determine the inlet state into an evaporating condenser based on the properties that we do know from our experiment. We recommend that you systematically tune one correlation at a time. It's very difficult to tune a model with many different correlations varying simultaneously. And so the methodology that we put forward and the flowchart that we've provided should give you a simple approach to tuning a heat exchanger that will be repeatable and that will give you the results that you see in the experiment. The parametric study feature within CoilDesigner can be extremely helpful in determining the right correction factors, and it's especially when we have data sets with multiple test points and we want to minimize error across the entire data set. I mean, you can use other tools like Excel or Ease to find the correction factors that will minimize error and help us to tune these models in a more automated fashion. We use airside heat transfer coefficient to tune our heat exchanger performance in terms of capacity. This is an assumption that we make. We could alternatively tune the heat transfer coefficient of on the refrigerant side, but the air heat transfer coefficient has a greater impact on the overall performance of the heat exchanger. So we find that to be a more effective and a simpler approach to heat exchanger model tuning. When we see large correction factors coming out of our model validation exercise, this is sometimes a warning sign. It can mean that there is either a problem with the correlation that's been selected, maybe our heat exchanger flow regime or geometry is outside of the range of what that author originally tested for their correlation, or it could even reveal that there may be some mistakes in our experiment. And so looking at the correction factors that have been selected, we can typically assess if there are any warning signs or any potential problems with our experimental results or our heat exchanger model. We recommend, obviously, you want to try to minimize errors in all of these values to the extent possible. We certainly want coil capacity to match very well, and that should always be, we should always be able to match that within about 5%. Air side and refrigerant side pressure drops are much more difficult to predict, especially through these empirical correlations that are being used. And so if those values are within about 20% or less, that's usually acceptable for most cases. But every application is different. In some cases, it's more critical to reduce these values even further. In other cases, an approximate value is appropriate. So this summarizes all of the recommendations that we would make in terms of the model validation process with CoilDesigner. We hope this session has been helpful, and additional information can be found on our website.